As we work to increase our proficiency in using NMR spectra to determine structures of unknown molecules, we've done some examples where you're given, like, here's a list of potential molecules, here's some spectra, which ones match. Basic exercise, particularly in learning how to use groups and integrations to gain a lot of information from spectra. Another classic one is to be given a chemical formula. And there you can use things like the index of unsaturations to help get you, a long way toward figuring out what the structure is. It can often tell you if the molecule is aromatic or cyclic or other interesting information like that. The more challenging ones come about when you don't have any of that nice, happy information, but you do have some information on the molecule. And one of the more common ones, because it is the end result of an experiment you could do, is to have the molecular weight. If you have an unknown, either a product from a synthesis or extract from a natural product that you got from something in nature, very often you will run a mass spectrum on it and have the molecular weight determined, and that's the type of question we're going to look at now. All of the spectra I show, as before, are linked in the description to the video or on the course website. And again, having the actual spectra in front of you on screen or on paper, in addition to what I present, kind of flash up on the screen here, can be really useful in seeing the fine details of some of the things that I want people to notice. Now, for this particular example problem, this is one I've used for a number of years. And the molecule, the information you're given in addition to a set of proton and carbon spectra for this molecule is the molecular weight. And so we have a molecule with a molecular weight of 144 grams per mole. Okay? Not a huge molecule, but not a trivial little molecule either, 144 grams per mole. And that's the extent of the information we have. And so one goal in mind, or one thing to try to do as you are working through this, is can you, from the spectra, determine at least a tentative chemical formula, okay, based upon the groups and integrations that you see in the proton and the number of carbons you see in the carbon spectrum. That is often valuable because you're trying to develop a formula that ends up having that molecular weight. And so when I'm confronted with a situation like this, and this is not an uncommon problem. I have an unknown with a set of spectra, and its molecular weight, is to see if I can determine the formula. And one of the best ways to do that is to actually look first at the carbon spectrum, okay, of this. So here is the overall carbon spectrum. Now we ignore, of course, the solvent peak in the carbon spectrum. Okay, there at 77 ppm. It is the deuterated chloroform carbon signal, so that we can ignore. And if we go through and count the number of carbons, and this is actually critical that you have either access to the actual spectra or expansions on the spectra or some information, because this is an interesting situation. When you look at the carbon spectrum, and if you count it carefully, if you see it here on the screen, you may actually miss the fact that there are two nearly overlapped carbons in this thing. One of them is a little bit easier to see. The other one, I really think you can only see it if you have an expansion or if you have access to the raw data and actually seeing this thing being processed on the computer screen itself, okay? And so here is what I'm talking about. This is the Upfield side of the carbon spectrum. And there's actually, you can see this signal is actually 2 carbons. And if you really zoom up here on the most upfield, my gosh, there are actually 2 signals in there. Those are 2 carbon signals nearly completely overlapped, okay? But as we've talked about with, the greater number of hertz per ppm in a carbon spectrum, overlap, while can be an issue in carbon is often, often they are still separated, but they are very close to each other. For this particular one, you really have to have either someone, when they're giving you spectra on paper, have an expansion in there, or have access to the raw data so you can zoom in yourself. But if you're careful with it here, you can count that there are 8 carbons, okay, in this molecule. There are 8 distinct carbons here, okay? And so a tentative chemical formula is going to be C8 something something. Always subject to change, but that's a good starting place. The next thing to look for is the proton spectra. And we see on the protons here, we see in the protons 5 groups. Okay. And they integrate with the ratios of 2 to 2 to 4 to 2 to 6. Okay, the 5 groups integrate this way. Very likely overlap going on here. In fact, if you look at the spectra, you can see that, they're the complicated signals that seem to have, fairly quite a bit going on in there. And so if you add all those up, you have 16 hydrogens, okay? And so we have a tentative formula, okay? C8H16. There's almost, there are very likely other bits in there, but we have this as at least a starting point. And what we do is we look at this and compare the molecular weight of C8H16 to the actual molecular weight given that is given in the problem, 144 grams per mole. And you add it up, C8H16 adds up to 112 grams per mole. So there's certainly more in this molecule than 8 carbons and 16 hydrogens. But there's a couple of things to really note carefully here. This is relatively close to the 144 grams per mole. That's going to give me an indication that there's not a lot of symmetry in this molecule. Remember, a symmetric molecule is going to have a simpler spectrum than the molecule of its size might imply. Symmetric molecules will come out with molecular weights of, 70 when it adds up to 144, where there's going to be, you get a molecular weight that's somewhere around half of the actual molecular weight, something like that. The fact that this one comes out relatively close tells me that there's not a lot of symmetry, and in fact the difference between these two numbers is 32, okay, 32 grams per mole. Now, I've had more than a few students who say, oh my gosh, there must be an atom of 32 grams per mole in there. They go running off to the periodic table and they see sulfur at 32 grams per mole. This is immediately declared that the formula must be C8H16S. Well, it's certainly possible, but be a little bit careful here. We're not, doing, really unusual molecules here. 32 can come from a lot of different places. In fact, there's a much more likely one. And so we're going to keep all that in mind, okay, that we've got 32 grams per mole to account for beyond the carbons and hydrogens. And now we start looking at, after groups and integrations, we start looking at some obvious chemical shifts. And there's a couple that should just leap right out at you, okay? Some of them are dearest friends in the proton spectrum, right around 4 ppm, okay? In the proton spectrum, 4 ppm, we see 2 hydrogens, okay? A signal integrating to 2. It's a lovely triplet. We're not going to worry about coupling patterns in this video yet, but we have 2 of them. So we know deep in our hearts that we have likely a CH2 group that must be attached to something and very likely attached to an oxygen, okay? That is the most common structural fragment that gets us that chemical shift, okay? So we have that, tentatively, we have that to think about, okay? And again, as I often do, I'm making notes and little sketches and pieces to myself and then start to work to try to get these pieces to come together into a coherent structure. An obvious chemical shift sitting on the carbon spectra, okay? And the carbon spectrum, you see a peak at around 174 ppm, okay? Now, that is most definitely the realm of the carbonyls. In particular, it is very consistent with an ester, okay? And right there, That is huge because that gives us strong indication that there are two oxygens in here. We have an indication of an ester, two more oxygens. And if we add that to our chemical formula here, C8H16O2, there is 32 grams per mole, the extra we needed. That is a molecule of 144 grams per mole. Put a couple of exclamation points around it because that's significant, okay? We have at least a tentative complete chemical formula to work from. All right. There's one other, I think, couple of obvious chemical shifts sitting there in the proton spectra. There's a group of, there's 6 protons, likely 2 methyl groups down below 1 ppm. So we have, in the proton spectrum, 2 CH3s at the end of a chain. These are the highly Upfield methyl groups, okay? That we have good indication of. There's one other chemical shift that is sitting in the carbon spectrum, or sitting in the proton spectrum, excuse me, that I think is significant, and that is right there around 2.2 ppm. Now, 2.2 ppm, this is one I save for the last because, again, that area around 2 is a complicated area. Lots of things can come in there. But in this particular example, you know, we certainly know this thing isn't aromatic or anything like that, but it, you know, we do have indication of an ester, and one of the things that comes in this area around 2 ppm is a group of hydrogens on a carbon next to a carbonyl, okay? And so that is consistent with this, CH2, carbonyl, O. Okay? And so these are a lot of the significant pieces we have available. And so now what we do is we start trying to take our pieces, and let's face it, there's other information in the spectra, but these are like some of the most obvious ones that a quick glance should get you this far pretty quickly. And now you start trying to tentatively fit this all together into a coherent molecule. And so what I'm going to do is start writing out my puzzle pieces here. And I am going to be pretty confident about this, that I have a molecule with that fragment, okay? That of the 8 carbons in here, here are 3 of them, here are 4 of the 16 hydrogens, and both of the oxygens. This I'm quite certain about. I'm also certain that there are methyl groups out here at the end, CH3, the end of a chain, CH3, okay? 2 of them. Now, again, in the proton spectrum, this thing integrates to 6, which is certainly not, protons on 1 carbon, okay? It has to be 2, and these are almost certainly the methyl groups that are so close together they're almost overlapped in the carbon spectrum, but so they're very similar to each other, far away from anything electronegative, but slightly different, enough that we can tell the difference between them. And we see the difference both in proton and in the carbon spectra. So here are the fragments that I'm almost certain about, okay? And this, taking an inventory of what we have so far, I've got 1, 2, 3, 4, okay, 5. 1, 2, 3, 4, 5 of my 8 carbons. So I have 3 carbons to go. I have both of my oxygens, and I have 3, 4, 5, 6, 7, 8, 9, 10. I have 6 hydrogens to go, okay? To go. Now, looking at the proton spectrum, we do have other signals in there, and indeed they integrate to, one of them integrates to 2, the other a overlap signal integrating to 4. Most consistent with 3 CH2 groups, okay? 3 CH2 groups. And so, putting the pieces together here, okay, we're going to insert CH2 groups in here, okay, into these pieces there. And in fact, the structure that I first came up with when I was doing this it was, let's see, this one. CH2. Now, I've inserted one of my CH2s here, so I'm going to insert 2 more over here. Okay. And there is a structure with 1, 2, 3, 4, 5, 6, 7, 8 height, 8 carbons, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 oxygens, hydrogens, and the 2 oxygens. So there is a lovely structure, okay, of the molecule. And perfectly consistent with the spectra. And in fact, this is the structure of the molecule, okay? It's something called butyrate. Okay. Butyrate, okay? And this is what I was expecting the students to come back with, and a number of them did. And I was, happy with that and ready to, walk off and go on to the next thing. And it suddenly hit me, and this is actually after using this molecule a couple of times in the past, it suddenly struck me, wait a minute. Couldn't I have put 2 of the CH2s over here and 1 of them there? Okay, this is like going 1 experiment too far. Couldn't I have done it this way? Put 2 of the CH2s over here. CH2, CH2, then I have my CH2, the ester, and then CH2, put the 1 CH2 on this side, CH3. And you look at those and you think, well, but they are very similar molecules, but they are different. Okay, they are not symmetric. They are, they're subtly different, and in fact, they would have different names. I'm fairly certain this one would be propionate. Now, I am not an expert on all that organic naming bull, so this is what I'm going to, these are my names and I'm sticking to them. Okay? But they are different. And it got me to looking at the spectra carefully to see, can I tell them apart from each other? Okay? Is there any clear indication that it's this structure and not that structure? And there isn't. As an instructor, I face a situation, I probably counted a few students wrong if they came back with this one, and I'm certainly, they just failed the class and it was over with for them. But I feel a little bit bad about that. Not too bad, but not really. It led me to a realization, this is actually a much more interesting problem than I had first thought. I thought it was a nice exercise in getting a molecular weight and a molecule that has some complexity, but not overwhelmingly so, that you could put a structure together, fairly readily. But it turns out this one is actually a bit more intricate than you might think. When you really start digging into it. There are other structures you could draw, but the coupling patterns really, that we get into later, really, I think, lead me to think that these 2 structures are by far the most likely from just the spectra as presented. But I realized as I was doing this that, I really can't tell these 2 apart. Now, there are a couple of things to do. One of them is to simply simulate the 2 molecules. Okay, and MNOVA, the program we use to process our spectra, has a very nice simulation routine, and there are websites out there that do this type of stuff. And so here are the 2 simulated sets of spectra, both proton and carbon. And the significant difference between them in the simulated spectra is the overlap of some of those CH2 groups. Now, the simulated spectra show that, in the butyrate, they're really close, but not quite as overlapped as the actual spectrum shows. In the propyl version, the overlap is much less, and so the hydrogen signals are actually distinct here. The fact that the simulator says the butyl is closer to being overlapped than the propyl, and what we see in the actual spectrum is they are badly overlapped, that's an indication that it is the butyrate structure. But to be honest with you, that's rather weak evidence. I might bet a student's life on that, but I certainly not bet my own that that's being absolutely correct. And so actually, it leaves us with a bit of a conundrum. How do you use NMR to tell the difference between these two molecules? Based upon simply the proton spectra and the carbon spectrum, you really can't definitively tell them apart from each other. And so I'm going to leave this particular video at that point, okay, with that realization that it was completely unexpected as far as I'm concerned. It's kind of an interesting one to see something new pop up in what I thought was, pretty basic, well-trod territory. Is solving an unknown when you have the set of spectra and a molecular weight. You determine tentative formulas, which gets you index of unsaturations, tells you about other atoms, get fragments together, and then to start putting the puzzle pieces together. It's a nice exercise in that. It turns out, yes, you can tell the difference between these two molecules using NMR spectra, and in fact, it makes what will be, I think, a really instructive introduction into some fancier NMR spectra that we get into later in the term. You can tell the two apart using a couple of the two-dimensional NMR spectra. And so we're going to come back to this topic later and using the 2D spectra to show how indeed the molecule that presented these spectra was butyrate and not the propyl version. Okay? Definitive evidence of how you can tell this structure apart from that structure using simply NMR spectra. Interesting problem. Okay? Didn't expect that to happen, so it's kind of cool that it did. Keep all this in mind about turning molecular weights into tentative formulas, fragments of molecules, and piecing them together. Practice a few of these on your own, and we'll talk to you later.